running north and south in the mid-Atlantic and in the Pacific, hot magmas are pouring out, renewing the Earth's crust. As these magmas cool, they contract and crack. Ocean water then penetrates down to the molten magma. The water heats and it rises. Sulfur and metallic compounds from the adjacent rocks dissolve in the rising water and they react. When the hot mineral-rich solution comes in contact with the cooler waters, a temperature difference of nearly 400 degrees, minerals precipitate out, often collecting in the cracks and fractures of the rocks.
They gave us direct visual proof that our ideas of the circulation of water around magma chambers and the stripping of metals from surrounding rocks actually is a valid process in the formation of hydrothermal ore deposits.
The third process by which ore and mineral deposits form is sedimentation. Sedimentation is a physical, not a chemical process.
Bits of rock and mineral matter can be carried by flowing water. In areas where the velocity of water is decreased, the particles of rocks and minerals that are carried by the flowing water may settle out.
Because they are at the surface and because they are relatively soft, sedimentary rocks have been mined, cut, and shaped throughout civilization. In many ways, sedimentary rocks have shaped our history. Our cities were built with them. We make roads, skyscrapers, and statues of limestone and marble. Our ancestors built with it too. They wanted their buildings to last, so they used rock. They couldn't have known the chemical environment would change to conspire against them.
Here we have a couple pieces of common sedimentary rock. They're limestone. They're both made of calcium carbonate. This limestone came from Indiana. This one is Italian marble. Again, both of them calcium carbonate. Now, we've used that material to build buildings, to make monuments, statues, but we have a problem now in modern day. Certainly you've heard of acid rain. Well, acid rain, the problem with that is the acid will react with that calcium carbonate, with that limestone, and cause deterioration of that substance. Let's do a test, and I can show you how that works. What I'm going to do is add a little hydrochloric acid to the limestone. Now, geologists use this as a test for limestone because you'll see why. There's certainly a reaction. Put a little bit of acid right on the limestone. Watch what happens. Whoa, see the bubbles coming off of there? Now, here's the marble piece. The Italian marble does the same thing. Of course, it should. They're both calcium carbonate. The reaction now that is happening is that the calcium carbonate reacting with the hydrochloric acid to produce carbon dioxide gas given off, as well as some water, and it's left in with some calcium chloride, some salt that's left on there.
Limestone and marble have always been important building materials, but they are both calcium carbonate. These sculptures and Renaissance buildings in Venice, Italy, are priceless treasures from our past. Because they are made out of marble, the past is crumbling before our eyes. These works of art are being exposed to acid rain, which reacts with the calcium carbonate, turning these sculptures into soluble calcium salts. The same chemical reaction involving acidic rain and calcium carbonate has been going on naturally for millions of years. It's how caves are formed. Although carbonate minerals are nearly insoluble in water, they are readily dissolved by the carbonic acid which is in the groundwater. As this diluted carbonic acid seeps through the joints of the rock formations, the limestone can be dissolved away. Over time, a cave is made. In this reaction, an equilibrium is reached. Calcium carbonate and bicarbonate exist together in the solution. It's a reversible reaction, which we can duplicate in the lab.
What if I took some of this calcium oxide, calcium carbonate, minus the carbon dioxide, and put it into this distilled water, just plain water? You form a cloudy solution of calcium hydroxide. Now, what could we do with this in an interesting way? Now, there's another process that goes on here. What if I took this solution, poured it through the filter paper there? I would then have a solution of calcium hydroxide, or really a solution of calcium oxide. You could look at it that way too. One of the things I can do, I can add that carbon dioxide back onto there. Let's see if I can add it back on. So I can take that filtered, I already did the filtering process for you, take some of this filtered solution of calcium oxide, really calcium hydroxide, a base, and blow into it. Now, if I'm not going to drink it, am I? I'm going to blow into there. So blowing in means now that I'm adding carbon dioxide. We breathe in oxygen, we breathe out carbon dioxide. Watch what happens. There it goes. Now the cloudiness is calcium carbonate. I've put the CO2 back onto that calcium oxide. Now let me speed this process up a little bit for you by adding in some dry ice. The dry ice is solid carbon dioxide, so it's a more concentrated form. Put that in there. I'm going to put quite a bit of it. So initially what you will see is that solution getting more cloudy. You're forming more calcium carbonate. But there's an interesting phenomena that occurs. And what that is that bicarbonate will be formed. Now the bicarbonate is soluble. It will dissolve in the solution. And hopefully we'll see it clear up. Now this process that we've talked about is a reversible process. We've shown a little bit of that. Calcium oxide into a water solution, and then we can add the carbon dioxide back into there. Oh look, it has cleared up. So now that we see that the bicarbonate must have been formed. Well, this sounds like a fairly complicated procedure, but it's really not that complicated. In fact, nature does this very, very well underground.
Here in Mammoth Cave, Kentucky, the same natural processes we saw in the laboratory are at work. Wherever the water drips, stalagmites form on the cave floor, and stalactites form on the ceilings around the source of the dripping water. The building process is slow. It takes over 100 years to form a single inch of a stalagmite or a stalactite. Another common compound, like calcium carbonate, which forms sedimentary rock and is found nearly everywhere, is silica, silicon dioxide, or as we know it, sand.
Sand. It not only feels good between my toes at the beach or running through my fingers. What a simple material and thousands of years of use. What is sand? Sand is quartz, finely divided, and quartz is a compound of silicon and oxygen, bound extremely strongly together. And it's only in this century that we've learned how to break apart that bond efficiently and economically, and to make large quantities of pure, very pure silicon. It's changed our lives. The silicon revolution is only 40 years old. Isn't it ironic? The new information age being shaped from simple sand?
Sand. It's even more common than limestone. It contains two of the most abundant elements on Earth, silicon and oxygen. Pure silicon doesn't exist in the elemental state, and it's been only recently we have been able to extract the silicon from the silicon dioxide. The new revolution of silicon technology has been built on these discoveries. If silicon and oxygen are the two most abundant elements in the Earth's crust, how do they combine with each other to form a variety of substances? And what structure do they have? A look at the basic structure of a silicate reveals a silicon atom covalently bonded to 4 oxygen atoms, forming a tetrahedron with the silicon in the center. This is the basic unit of silicate minerals. 2 tetrahedra can link together by sharing an oxygen atom. A chain starts to form as 2 oxygen atoms are shared by 2 silicon atoms. This chain is the unit in fibrous silicates, like asbestos. 2 chains might link together, with every other silicon sharing oxygen atoms.